be going through paper 2 of the May-June 2023 grade 12 exam. We'll be going through paper 1 and we'll be starting with question 2. So our question 2.1 gives us a geometric series 1 over 5 plus 1 over 15 plus 1 over 45 plus all of that. 2.1.1. Is this a convergent geometric series? Justify with the correct answer. Now, we know from our classwork that the common ratio for a geometric series is given by 1 over 15, which is the second term, divided by 1 over 5, which is the second term, or 1 over 45, the third term, over 1 over 15, the second term. And this will give us 1 over 3. Now, from this, since our answer for R lies between -1 and 1, we can say that the series is convergent. 2.1.2. So 2.1.2 tells us to calculate the sum to infinity of this series. Now, the sum to infinity is given by S infinity is equal to A over 1 minus R, where our R is the common ratio. Now, A being the first term, this is A, which is substitute that in as 1 over 5 over 1 minus 1 over 3. Plug that into your calculator and that should give you 3 divided by 10. Thus, your sum to infinity is 3 divided by 10. I'm just going to make the screen a bit bigger so that we can work nicer. Now, 2.2 and arithmetic and geometric series are combined to form the pattern, which is given by Pn. And our Pn is, okay, let me write that down, 2.2.1. What is our Pn? Our Pn is, okay, I'm just going to write that here so that I can just quickly just copy it where I need to write it. X 1 over 3, 2x 1 over 9, 3x 1 over 27. We cut that. We come back and paste. All right, fine. So we are told, what are we told to calculate? We are told to calculate, we are told to write down the next two terms in the pattern. And looking at our pattern, we can clearly see that the next two terms, 2.2.1, the next two terms are going to be 4x and 1 over 3 to the power 4, which is approximately, and what is 1 over 3 to the power 4? 1 over 3 to the power 4 is 1 over 81. 1 over 81. Those are the next two terms in our term, in our series, in our sequence, please excuse me. A sequence. Now write down the general term Tn for the odd terms of this pattern. Now, for our odd terms, what we're going to do is we are going to now come and say 2.2.2. We are going to start now with the formula. The formula tells us that Tn, right, is equal to, now seeing as this would be Tn is equals to A plus b n minus 1, right? Now, we know that our a is given by x, is equals to x, right? And b is also equal to x, okay, into n minus 1, such that you have x plus xn minus x. These two cancel each other out, such that we are left with xn. The third question, what does the third question want us to do? Okay, we are going to 2.2.3, right? 2.2.3, we are asked to determine t to the power of 36. T to the power of, no, sorry, we are told to determine p26. P26. Now, p26 will be given, let me just write that down. P26 will be given by T13, right? Now, the reason we say it's going to be given by T13 is because this is going to be the 26th point in our original sequence P will be given by the 13th term of the arithmetic sequence. Now, why is this? This is because our P sequence is given by the arithmetic, T arithmetic plus T geometric. Now, because P is a combination of these two, we can therefore decide to check whether we can therefore decide to assign a half value for one of the substitutions, right? For one of the terms, for one of the series or the sequences, for one of the sequences essentially, right? We can thus pick out one of the sequences to have a 13th term, which is half the number of terms that we would need for P26, right? And for simplicity, we will choose the geometric term. Now, we know that the geometric sequence is given by Tn is equal to AR to the power n minus 1, right? And we know that the first term in our geometric sequence, which is essentially the geometric sequence, is thus 1/3, right? And the ratio between them, because 1/9 divided by 1/3 is equals to 1/27 divided by 1/9. Thus, we can therefore say our ratio R is equals to 1/3. Is that understand? Now, since we can then substitute that into our formula to say that our ratio is equals to 1/3, and n, since we are looking for T13, n is equals to 13, and then we minus the 1. That gives you that T13 is equals to 1/3 all to the power of 13, which is approximately 6.27 times 10 to the minus 7, or it's equal to 1,594,323. Quite the small number. And going to the next question, 2.2.4, if the sum to 21 of Pn is equal to 33.5, then determine the value of x, right? So that's going to be 2.2 0.4. We are asked to determine the value of x if P21 is equal to 33.5, right? Now, what we're going to do is we're going to say, remember what I said about P26? I told you that P, the sequence P is given by the sum of your geometric and your arithmetic sequences, right? So now this essentially tells you that the sum 221 of n equals to 1 for Pn is given by S11 plus S10, right? Which are our series, right? This is going to be for the arithmetic term. This is going to be for the geometric term, right? Okay. And now we just plug in. We know the formula for our arithmetic is given by xn. Therefore, we can come back and say this is equal to xn okay, let me just do the substitutions, right? I'll just do the substitutions. Now, this is going to be equals to 11 over 2 into 2x plus 10x, right? And our geometric term will be 1 over 3, 1 minus 1 over 3 to the power 10, all over 1 minus 1 over 3, okay? This will simplify then to 66x plus 0.5, which we equate the side to 33.5, right? Now this then tells you that 66x is equal to 33.5 minus 0.5, which is equals to 33, such that x is equal to 1 over 2. And there we are. We have our answer. Moving on to question 3. So question 3 is also a question about sequences. It's also a question about sequences, and in this case we have a quadratic sequence. We are told that the second difference, we are told that the quadratic sequence has the following properties. The second difference is 10. The first two terms are equal, and t1 plus t2 plus t3 is equal to 28. Okay? So from this information, okay, let's just write down what we know. We know that t1 equals to t2. We know that second difference d2 is equal to 10. And we also know that t1 plus t2 plus t3 is equal to, what was that equal to again? That was equal to 28. Yes, 28. It's equals to 28. Now the first question, 3.1. What does 3.1 want us to do? 3.1 tells us to show that the general term of the sequence is given by Tn is equals to 5n squared minus 15n plus 16. We are asked to show that RTP, which just essentially means required to prove. We are required to prove that Tn is equals to 5n squared minus 15n plus 16, right? Now, this is our RT and how do we do that? The first thing that we're going to do is we are going to look at the information that is given to us in the problem statement. Now, the first thing we are told is that the first two terms are equal, so I can just write that out as, okay, let me just use a different color here. x, right? And we know that this is t3, right? And we are also told that the second difference is 28, but we can then make the intermediary step to find the first difference. X minus x is 0, t3, this is going to be t3 minus x, right? And the second difference, sorry, I will also use a different color there. The second difference is equal to 10. Okay, now let's start by solving, right? Our formula tells us that 2a is equal to 10 such that a is equal to 5, right? This comes from formula, this comes from stuff that you've learned in school, this comes from stuff that you've learned in class, right? Fine. Then moving forward, we will then come and say 3a plus b is equal to 0 such that 3 into 5 plus b equals to 0, therefore b equals to minus 15. All right, wonderful. Now, using what we know about sequences in series, what we are going to do is we are going to take this term, right, and subtract this term and then equate to this term. So essentially, let me just show you what I mean by that. I am saying we are going to say t3 minus x minus 0 is equal to 10, which thus tells you that t3 is equal to x plus 10, right? Now, since we have figured out that a is equal to 0, and we know that a is also, okay, let's leave a alone for now. And let's go on to the second one, right? The second step in our solution. The second step in our solution will be to figure out what the value of x is, right? So now, the value of our x will then be this term plus this term plus this term, which is essentially going to be the three first terms equated to 28, because that is what we are given in our problem statement. We are told that t1 plus t2 plus t3 is equal to 28. And we already know that t1 and t2 are equal to x, right? Because we have decided to name them x. So what we're going to do now is we're going to say 2x plus t3 is equal to 28. Where does this come from? This comes from t1 plus t2 plus t3, which is equals to x plus t3, right? Now, since we know this, and we know that t3 is equal to x plus 10, right? Let's name this equation 1, and let's sub 1 into 2, and we will name this 2. When we substitute that, this will give us 2x plus t3, that will be x plus 10, which is equal to 28. Working this out, this will give us 3x plus 10 equals 28. What's 28 minus 10? That's 18, such that x is equal to 18 over 3. X is equal to 6. We have found our value of x. And since we have found our value of x, we can thus say a plus b plus c is equal to the value of x that we have found, right? We have, which is essentially the first term in our sequence. And we know that our a is equal to 5, our b is equal to minus 15, and thus we don't know the value of our c. we can substitute that in to say 5 minus 15 plus c equals to 6. This tells us that c equals to 16. Let me just move that this way for better coherence. Wonderful, wonderful. So because we have our a, b, and c, we can therefore come and say Tn is equals to, you know how the general term for a quadratic sequence is given as an squared plus bn plus c? That was basically the point for trying to find the a and the b, and then using the value of the first term in order to find c, right? So the reason for that is essentially so that we can substitute that into the general formula to give us a equals to 5 and squared plus b, sorry, that should be a minus, b is equals to minus 15 and c equals to 16. Plug that into your calculator and you will find that the answer is plug n equals to 1 into the calculator, and you will find that the first term in the solution is indeed 6. Now, the next question in our the next question in our series of questions will be 3.2. Is 216 a term in the sequence? Is 216 a term in the sequence? Now, how are we going to solve this one? Now, the best way to solve this one is to immediately, right from the bat, equate our quadratic series or our quadratic equation for the series to whatever term that we are trying to figure out if it's in the series or not, or if it's in the sequence or not, right? Now what we're going to do is we're going to take 5n squared minus 15 plus 16 and equate this, minus 15n, sorry, plus 16 and equate this to 0, right? Now, sorry, we do not equate to 0, but rather we equate to 216. When we transpose the 216 to this side, we will find that 5n squared minus 15n minus 200 is equal to 0, right? From here, we can see that 5 is a common factor, and because 5 is a common factor, we can remove it so that we are left with n squared minus 3n minus 40, which is equal to 0. On this side, we also divided by, on the right hand side, we also divided by 5, and 0 divided by any number, as we all know, is equal to 0, right? So from here, we are going to try and find the factors of 40 and 1, the factors of 40 and 1 that can give us a negative 3, and that just happens to be a negative 8 and a positive 5. Negative 8 and a positive 5. Thus we will have n minus 8 and n plus 5 being equal to 0. From here we have our critical values such that n equals to 8 and n equals to minus 5. But now here's the funny thing, right? We are looking for a term in the series, and it doesn't make sense for the term in the series, for a term in the series that looks like, for the term in the series, it doesn't make sense for the term in the series or for the nth term in the series to be a negative number, right? So what I'm trying to say is n cannot be negative. You can't have a term negative 5, right? You always have the first term, the second term, the third term. You don't have the 0th term. You don't have the negative 1th term. You don't have the negative 2nd term. You only have positive integers for where you fall in the sequence, right? Therefore, our n cannot be equal to 15. And to To essentially just confirm this, you can just plug in n equals to 8 and see if it returns 216, and because of that we can then conclude that 216 is the 8th term in our sequence. Beautiful. Moving on to question 4. Given the function px is equals to 1 over 3 all to the power x, right? 4.1.1, is p an increasing or a decreasing function? Tricky one, right? Question 4, 4.1.1. Now, we usually expect functions of the form f at x is equals to a to the power x to be increasing. All right, we expect them to be increasing. Now, it's very important to remember that in this case, our a is a fraction, and because of that, our function will be decreasing. It will act opposite to if it was not a fraction, if it was a whole number, because if you look at it, f at x is equals to 3 to the power x is not the same. It does not increase the same, or it does not increase the way, or it does not decrease the way that f at x is equals to 1 over 3x does, right? So this just clearly tells you that your function begins from a very small place. It begins from a very small function value, and it does not increase, because the bigger the denominator gets, the smaller our function value. The smaller our function value is. Therefore, we can reason that y is equal, sorry about that. We can reason that f at x is equals to 1 over 3 to the power x is decreasing. While it is still a positive function, it is asymptotic. And okay, let's leave asymptotes alone for now. But yes, this does become asymptotic at some point, but we'll leave that alone for now. 4.1.2. Let's look at the question. Determine p to the minus 1, the inverse of p in the form y equals to. That should be already obvious to you what you must do. The first thing you do, obviously, is just write down your formula or your equation to the power x, right? Now, here's the beautiful thing about such questions. They allow you to play around with the variables. The next thing that you do in order to find the inverse is to swap x and y, right? You swap x and you make it a y, and whatever is x, you make it an, whatever is a y, you make it an x, and whatever is an x, you make it a y. So here we will have that x is equals to 1 over 3 to the power y, such that y is equals to the log of our base multiplied by our variable x, right? An alternative way you could do this is you could write y being equal to 3 to the minus x, because this is exactly the same as writing 1 over 3 all to the power x. It's exactly the same. Now what you're going to do again is you are going to swap x and y. Now your x will be equal to 3 to the minus y in such a way that now y is equals to minus. Okay, let me do this step by step so that you don't get lost. You will have that minus y is equals to log 3 of x, and y will then be equals to minus log 3 of x. Wonderful. And next question, we were asked to write down the domain. Okay, I'll just do the next two questions. The 4.1.3 asks us to write the domain of p to the -1, and 4.1.4 asks us to write the equation of the asymptotes of p at x minus 5. P at x minus 5. Okay, so let's start with 4.1.3, our domain. The domain for this one is pretty simple because your graph is an increasing function, right? I mean, sorry, your graph is a decreasing function, but it does not approach, it does not equate to 0, right? It does not equate, your x cannot equate to 0, right? Because then that means your function is just 1. So now what we're going to do is, for our domain, is we're going to say that our domain is x greater than 0, such that x is an element of real number, right? Because your x can essentially take on any value. Your x can take on literally any value. Although, yes, your x can take on literally any value that is above 0, and as long as it's above 0 and is a element of real numbers, then it suffices as the domain. And 4.1.4 asks us to write down the asymptote of p at x minus 5. Now, p at x minus 5 is equal to 1 over 3 to the power x minus 5. And clearly from here, you can then see that our asymptote is given by y equals to minus 5. We good? We good. 4.2. 4.2 gives us a very beautiful equation, a wonderful equation in the form of a hyperbole or a hyperbolic function. We are given f at x is equals to 4 divided by x minus 1, all plus 2. Write down the equations of the we're going to do the first two questions immediately. Actually, we'll just do the first three questions immediately. I'll just read them out and we'll work on them right from the get-go. So we are told to write down, firstly, we are told to write down the equations of the asymptotes of f. Secondly, we are to calculate the x-intercept of f. And lastly, we are to sketch the graph of f, label all asymptotes, and indicate the intercepts with the axes. Now, let's go on to the first part of our question. Let's write down our equation. F at x is given by 4 over x minus 1 all plus 2, right? The first thing we need to do, 4.2.1, the first thing we need to do is to write down the asymptotes. Immediately you can tell that for a function given as f at x is equals to a over x minus p plus q, the asymptotes are given by x equals p and y equals q, right? So this immediately tells us that our asymptotes are thus x equals to 1 and y equals 2, right? Wonderful. 4.2.2, we are asked to find the x-intercept of our function, and in order to find the intercept or the x-intercept of a function, what do? We equate our function value to 0. And by equate our function value to 0, I mean we just take f at x to be equal to 0, which tells you that 4 over x minus 1 plus 2 equals 0, right? Basic algebra, we have 4 over x minus 1 equals to minus 2. And then now what are we going to do? We are going to multiply with x minus 1, and we are going to multiply this side again with x minus 1, such that these two cancel each other out, and we are left with 4 is equals to 2, negative 2 into x minus 1. Now I'm just going to flip this around so that it allows for better flowability. I'll write this as minus 2x minus 1 is equals to 4. Expanding my bracket gives me minus 2x plus 1 equals, plus 2. This should be a plus 2 equals 4. And minus 2x equals 2. X equals negative 1. And that is our x-intercept. 4.2.3 is asking us to sketch the function. All right, sketch the function. Now I will sketch our function. Let me just do this. No. And then I'll just make that a line. Fine. Okay, so the first thing we'll do is we'll write down our asymptotes. We know that the asymptotes are given by x equals to 1 and y equals to 2, right? So let's label those. Let's write this as 1, and let's label this as 2, right? And from this already, we can, okay, I'll use a different color for the asymptotes. We can just immediately show our asymptotes to be these two. Here are our asymptotes. So what this tells you is that your first graph is going to be on this half, right? Or this quarter of the Cartesian plane. And, okay, but this is a bit unclear. So I'm gonna just write this in a much better way. 1. Let's put the 2 here so that our asymptotes will be here. And here. I think this is a better picture. Your graph will come off this way. Please excuse my drawing. I am horrible at drawing. And now for the intercepts. When y is equals to 0, we know that our x equals to minus 1. What about the situation where x equals to 0? This tells me that f at x equals to 0 will be given by 4 over 0 minus 1 plus 2, which is going to be minus 4 plus 2 is equals to minus 2. So meaning our y-intercept will be minus 2. That tells you that your graph needs to pass through these 2 points. Again, please don't mind the drawing. It's not really that important, as long as it's not really as important for it to be beautiful, as long as I can show that this is my graph of f at x. And let's look at the last few questions. The last few questions are asking us to A, use the graph to determine the values for which 4 over x minus 1 is greater than or equals to 2. This is an inequality. And the last question asks us to determine the equation of the axis of symmetry of f at x minus 2 that has a negative gradient. Okay, so 4.2.4, let's solve our inequality. We are trying to find a place for which f at x is greater than or equals to minus 2, right? So we're going to substitute our value for f. Please excuse me. What did the question say? Let me look at the question again. Oh, we need the values for which 4 over x minus 1, not f at x. So please excuse that. We need values for which 4 over x minus 1 is greater than or equal to negative 2. Immediately transposing, we can then say 4 over x minus 1 plus 2 is greater than or equal to 0, right? And from this working, as you can see, this is the same working that we went through in this part of the question, right? This is the same working that we went through in this part of the question. And now, when you look at what this right-hand side of our inequality is, it's exactly f at x. It is exactly equal to f at x. Now, because it's equal to f at x and we already have f at x drawn, we can just look for places that satisfy our inequality on our Cartesian system from 4.2.3. And what I mean by that is we are going to look for points on our graph where our graph is below 0, right? And our graph is below, we need our graph to be below this line. Okay, let me pick a different color. We need it to be below this line, this y equals 0 line. And where does that happen? That only happens when we are looking for the point where it's greater than 0, not less than, greater than 0. Please excuse that slip of the tongue for a bit there. We are looking for points where our function value is greater than this 0 line. And immediately we can see that for situations where x is greater than minus 1, right? We know that x must be greater or equal to minus 1, right? Because this is a point on the Cartesian plane, right? This is a point on the Cartesian plane, and 0 is neither positive or negative, so that's why we include this x greater than or equal, x less than, this should be less than, x less than negative 1. And when we look at the other side of the graph, we can tell that immediately after our asymptote, our function value is greater than 1. Therefore, we choose the part where x is greater than 1. Now, the reason why we choose x greater than 1 and not x greater than or equal to 1 is because our function does not have a value at x equals to 1. Our function does not exist at x equals to 1, which is why our inequality is not inclusive, right? So we will come back down and write that, and when we write that down, we'll just say x must be smaller than or equals to minus 1, or x must be greater than 1. That is in our inequality solved. So for question 4.2.5, okay, this was a bit of a mouthful, so I'm just going to look at it again. Determine the equation of the axis of symmetry of f at x minus 2, right? That has a negative gradient, right? So the first thing that we're going to do is we're going to write down the equation for the axis of symmetry, and the equation for the axis of symmetry is always a straight line that has a negative gradient in this case. So this tells you that our equation of the axis of symmetry is given by minus x plus c, right? And we are arbitrarily choosing to have m, our gradient, be equals to minus 4, to have an absolute value of 1. But it could be any value, but in this case, because it's an axis of symmetry, our m, or our gradient, is going to be negative 1, right? Now, the point of intersection for our graph, the point of intersection of axes for our graph, for a situation where we are looking for the axis of symmetry, will be the point x equals to 3 and the point y equals 2. Okay, our axis of symmetry will point there. We substitute this point into our equation such that we have 2 is equals to minus 3 plus c, and c equals to 5. This tells you that the equation for the axis of symmetry is minus x plus 5. Okay, wonderful. Now, there is a different way in which you could do this, where you could essentially use a much more complicated form of the straight line equation, where you have y being equals to negative because of the gradient, remember, x plus p all plus q, right? Now, what we're going to do is we are going to, for where we see x, we are going to substitute in we're going to substitute in x minus 2, okay? Such that we have this being equals to minus x minus 2 plus, right? Now, our p, we know this to be minus 1. And our q is 2. Although our p should be, although the p should be a positive 1, we are taking it as is from the formula, right? Because the formula states that the formula for a hyperbolic function states that any hyperbolic function, f at x, has the form a over x plus p plus q. So in this case, because our denominator has a negative in the middle, we can just then take p to be equals to negative 1, right? But it doesn't work the same for when you're looking for the asymptote. It doesn't, for the asymptote, you take the absolute value of p, which is 1, okay? Fine. Okay, moving on, doing your algebra, this will give you into negative x minus 3 plus 2, and this will be minus x plus 5. And ladies and gentlemen, this is where we will leave it. And next time we will be doing question 5, question 6, and question 7. See you next time.